Buenas tardes a todas y todos. Vamos a dar unos minutos porque ya estamos por comenzar, porque ya estamos por ahí saliendo en plataformas virtuales, así que vamos a dar entonces inicio. Si las personas por ahí en el Teatro Californix nos dan señal, vamos a comenzar. Professor Amy and Dr. Yu. Muy bien, entonces creo que ya estamos por salir en las plataformas. A todas las personas que nos acompañan desde el Teatro Californix, agradecerles su presencia y su participación y vamos a dar entonces inicio con esta primera conferencia al margen del primer Congreso Internacional en Agua Limpia y Saneamiento del TECNM, la primera conferencia virtual, pero la segunda conferencia plenaria de todo el evento. Tendremos como moderador de esta conferencia al Dr. Yu, quien nos acompaña desde Canadá, y a la profesora Amy Bilton, quien será nuestra ponente magistral. Saludos a todos desde el Instituto Tecnológico de Tijuana, que pertenece al Tecnológico Nacional de México. Dr. Yu, this is your auditorium.
Y marginadas. De manera más amplia, su trayectoria académica impulsa el desarrollo de sistemas modulares y resilientes de purificación del agua, en zonas periurbanas y la investigación colaborativa con comunidades indígenas para el desarrollo de la infraestructura sostenible. Su liderazgo en la ingeniería con impacto social y global ha sido reconocido ampliamente con numerosos premios, entre ellos the University of Toronto Global Educator Award, el MacLean Award y más recientemente su elección como Fellow of Canadian Academy of Engineering. Más allá de estos reconocimientos, quiero también compartir una nota personal. Tuve el privilegio de trabajar durante 5 años bajo la dirección de la profesora Bilton como investigador postdoctoral en el Center for Global Engineering. En ese tiempo pude ver de cerca no solo su compromiso con el desarrollo de tecnologías sostenibles, sino también su capacidad para orientar y sobre todo para inspirar y motivar a los colegas y estudiantes y para construir una comunidad de práctica. Hoy nos compartirá la conferencia Innovating for Impact, Engineering Sustainable Water Solutions for Marginalized Communities. Les invito a dar una cálida bienvenida a la profesora Amy Bilton. Amy, you have the floor. Thank you.
Muchas gracias, Hugh. Very sweet, very sweet. So, buenas tardes, mi nombre es Amy. Es un placer para mí contarte un poco sobre mi trabajo. I wish I knew Spanish better, so I'd be able to do this entire talk in Spanish, but unfortunately, I need to rely on my English for a talk that's this in depth and this long. And I also saw some pictures of the auditorium before, and it looks like it would be an amazing space. So I really wish that I was there with you. Yeah, but family considerations kept me at home today. But I'm really happy to be able to share some of our work, thinking about water and being able to improve quality of life in marginalized communities. And really, a lot of the focus of the work I'm going to talk about today is really grounded in the Sustainable Development Goals, and in particularly Sustainable Development Goal number 6. And these are two of the sub goals of Sustainable Development Goal 26, which was established back in 2015. Was that 6.1 is looking at by 2030 being able to achieve universal and equitable access to safe and affordable drinking water for everyone, for all. And 6.2 is looking at being able to achieve access to adequate and equitable sanitation for all. And although these have been, were started back in 2015, really with the goal of reaching this by 2030, and there's been a lot of research and a lot of work that's been, pushing the Sustainable Development Goals, we're still not quite, getting to where we need to be. This is just a figure from a few years ago, looking at progress towards these goals. And we're still talking about billions of people that don't have access to these essential services, essentially access to water and sanitation and hygiene. And what makes this even harder is that when you think about the concentration of where many of the lack of access to services is, this is just a figure showing, just looking at safely managed drinking water. And if you look at this, you'll notice that many places in the global north do have, or in these dark blue colors, have wide coverage of safely managed drinking water. But there's a high concentration of places which don't have access in the global south, talking about sub-Saharan Africa, talking also about Latin America as well, Southeast Asia, are where this is a lot of concentration in terms of where there needs to be a lot of action towards achieving Sustainable Development Goal number 6. There's been a lot of work developing different technologies, trying to push towards this, but for some reason, a lot of these technologies aren't having the impact that they're meant to. There's been a lot of research and development in terms of developing improved toilets. But still nearly 2 billion people lack access to basic sanitation. And rely on the types of toilets that you see in the image here. This is a picture from some of our field work of a pour flush toilet that we're thinking about, other more sustainable options to be able to fit within this infrastructure. Another case is just in terms of thinking about access to water. There's a lot of work thinking about water access, and this is an image from one of my trips in Africa, which is very typical. In Africa each year, there's about 60,000 hand pumps that are installed, but about 66% of them will fall into disrepair. This is a really big problem. A lot of people have been thinking about different technologies to fill this gap, but there's often, it's a really challenging problem, very multifaceted. It's a technical problem, it's a social problem. It's there's many pieces which come together. And it's, when you're thinking about these types of solutions to solve these problems, it's really complicated. A good case study that really shows how complicated and nuanced some of these types of things can be is shown by the case of the play pump. And I don't know if many people in the audience are familiar with this particular case, but at first glance, this is something which you might seem or might feel is really potentially a great idea, right? And actually that's what happened. This was an idea which was presented first back in the late 80s at an agricultural fair in Africa. And the idea is quite simple, right? There's a lot of places that lack access to water, and there's a lot of places where kids also, they need something to do, they need some place to play. The idea behind the play pump was to try to put those two things together. The idea is that you would have a merry-go-round, which would be, the kids would be able to push and then spin around. That would pump the water up to an elevated water tower. And then later, when someone needed to come get water, they could open the faucet and get some water and be able to take it home to their household. And a lot of people thought this sounded like a good idea at the time. It won some World Bank Development Awards. It got funding from the Clinton Foundation. It was really well received. But in the actual, there's many elements of this which make it a big challenge. One is that when you look at this particular problem and you think about it really from a fundamental point of view, how much time during a day would kids be spinning around this play pump? They might spin around for maybe 10 minutes. So in order to pump that much water in 10 minutes, it would need to be crazy efficient. So people have done analysis on this play pump, and they actually found to be able to pump enough water to supply the actual needs of the communities it was meant to, it would need to be almost operated for 24 hours a day. So from an engineering perspective, the design of this didn't make any sense. From an implementation perspective, it also didn't make a lot of sense because, imagine the kids will use it for 10 minutes a day. What happens, if someone arrives at this watering point and there's no access to water? It's usually a woman who's collecting that water. They would arrive and they would have to basically spin around a kid's merry-go-round to get the water that they needed. So this is, from a social perspective, very degrading and a big issue. And then there are other issues as well in terms of the implementation. So this was seen as a big failure in many respects in terms of really, sounds like a great idea, but not really understanding the full problem and thinking about the holistic design when thinking about, not only engineering design, but the actual implementation as well. So in my work and in the work that we're doing in my group, we try to think very holistically about not only the problem and the technology, but how it fits into the particular location and the structure. Many technologies which have been developed really miss the mark, and they don't really address what is the core problem. So really, when my work, we think about really trying to understand fully what the problem is, and not just try to stitch something into a particular context, but really trying to think about defining, that problem and being able to think about which technology has the most potential to make an impact. Sometimes that involves developing something new, which really comes from fundamental elements of that problem. My group, we do a wide range of things and work on a wide range of different technologies, from thinking about technologies for improved water treatment and actually thinking about materials for those types of technologies, from desalination and foam-based adsorbents, to thinking about integrated energy technologies, to thinking a little bit about how water can be used more efficiently in agriculture, and to also thinking about the overall design of these types of systems and doing it in a way which is going to gear the technologies to have the most impact. I'm going to focus in on some technologies in the last two categories in the talk today, and these are projects which are currently ongoing and things that were really our current topics within my own research group. So I'm going to start by talking about some of the work that we've been doing, thinking about smallholder farmers and thinking about using water efficiently for many of these smallholder farmers. And in the initial phases of this work, we were actually doing some collaboration with some communities down in Nicaragua. And in Nicaragua, there are communities which have very large and long dry seasons. But many farmers were actually setting up their own technologies to deal with these types of conditions. So this is an example of one of those farmers who had installed their own very simple drip irrigation, was doing some reforestation, where they had these bottles with small holes in them that were dripping water at the base, and also had set up his own diesel-powered pump to pump groundwater up to an elevated tank that then he could put through drip irrigation on his farm. So Juan was someone who was really progressive in thinking about farming, but one of his big concerns, it was very intensive for him to get water from the ground, and he didn't know how much he really needed to be able to water his crops. He was doing it a little bit ad hoc. And as it was something which was really energy intensive and hard for him to be able to access the water, he wanted to think about how he could do this in the best way. So this was, a problem we spent a lot of time going through interviewing many farmers in this area, approximately 50 to 60 farmers, to try to understand that context. And many of them were mostly subsistence farmers, and we're using, we're transitioning towards these type of drip irrigation systems. They didn't necessarily have a stable access to electricity. They didn't have a whole lot of electrical tools or expertise, but they did have a lot of knowledge about how to set up and use plumbing systems in their particular farms. So we worked and we defined this problem. And being engineers, what we'd like to do in my group is we'd like to start just really understanding the physics of what's going on when growing these crops and irrigating these crops, to see what we could think about for some sort of sustainable technology which could improve Juan's or this different farmers water efficiency and water usage. And when we were actually looking and understanding the fundamental physics, we looked at what was going on in the soil. So as plants grow in the soil, they have to be able to pull the water out of the soil in order to grow. And they have to pull with a pressure which is bigger than something which is known as a soil water potential. So if the soil is really, really dry, there's very little water in that soil, and the plants are able to draw up. The plants like it to be with the soil to be somewhat moist, and the plants, where they usually like to grow, they'll need to be pulling with a pressure of around 30 kilopascals. And then if the soil is completely, saturated water sitting on top, it's going to be having the soil water potential of 0 kilopascals. So we were thinking about this. We learned about this property, soil water potential, and recognized that this is essentially a pressure. And we thought to ourselves as mechanical engineers, is this something that we can exploit when thinking in an appropriate technology for irrigation? One which would meet the constraints of having little, no really use of electricity, no electrical tools or expertise, and just some very basic kind of plumbing kind of knowledge. And we were able to develop a very simple mechanical concept which could regulate the water usage for this particular concept, this particular case. And I'll show you just a little bit in terms of how the fundamentals of this technology works. So the idea behind this system is that you have your irrigation for your system, and we have an irrigation controller which actually has this valve here, which can control the water coming from an elevated water tank to the drip irrigation network. And this valve is controlled using this very simple mechanism. So what we have is we actually have a ceramic tip buried down in the soil, and then it's connected to a water column and a water reservoir here. And what happens is this controller sees very similar forces to what a plant sees. So if the soil becomes dry, what actually happens is that water is drawn out through this ceramic tip, and that change in then pressure will pull back and open up this mechanism, allowing water to flow from our elevated tank to our drip irrigation network. And then when the soil becomes damp, it essentially goes in reverse, and water will flow back in, and the valve will close. So the idea is that we can create essentially a irrigation controller which uses the same forces a plant sees to be able to regulate water flow into the irrigation network. So we're in the process of actually building this out right now and showing its efficacy and doing some work with farmers to understand how this would be adopted. This is showing some of the testing which we've done. This is the first testing that we were doing in a greenhouse in Toronto, where we actually installed the controller and compared the usage of the controller to a simple timed irrigation network and timed irrigation system. And this plot on the left shows the basic operation of the system. It shows as the soil pressure goes down, the controller pressure also decreases, and then the valve opens, and then water flows into the soil, and the pressure goes up, and the valve will close again through this kind of pattern to regulate really that water flow into the irrigation in a way which would match the crop's needs. We've also done some studies to look at what will happen when we actually go and take this out to a larger plot and compared that to standard kind of timing if you'd have some timed irrigation. And we took some real weather data from a site in Toronto and did this comparison between timed irrigation here on the left and our passive irrigation controller. And you could see, in this case, there was actually some rain which was happening at the same time. So our irrigation controller over this course of 7 days only had to open 2 times to be able to kind of maintain soil moisture, and was able to save about 75% of the water usage over what the farmer at that particular site was doing with the irrigation, which was basically using this just standard irrigation, a timed irrigation, a certain amount of time every day. So we're in the process. This is a project which is currently ongoing within my group. We're in the process right now of actually refining the design of this valve and doing some things to make it so we can do adjustments in the operating pressure. And then also planning for a local field test. And then we've also developed a partnership with a UN agency over in Morocco, which does work with farmers. And we will do a controlled field test also with that UN agency over in Morocco to assess the performance, as well as do some adoption studies with farmers to try to understand what their opinion is of the design, as well as what would be some barriers towards those farmers taking up and adopting a design like this one. So this is an example of one of these types of projects which we're doing in our group. And now I'll talk about another project going on within my group, which is actually looking at sustainable sanitation. And this is some work of a recently graduated PhD, Pablo Cotara, and he was thinking about sustainable sanitation for sites, and he was actually working in thinking about many communities, actually also in Mexico, which lack piped water and sewage. This is a picture that he took in some of his own field work in and around Mexico City. So in Mexico City, there are many places, which are like the one in the image that Pablo shared here, which lack piped water and sewerage and are actually prone to flooding because of the high groundwater table, and also have relatively high medium to high population density. So this is a challenge for these sites without this piped sewerage. So he was exploring more if dry toilets could be a feasible sanitation solution in these particular sites. And, through some of his initial feasibility studies, he saw maybe it could make sense. These types of dry toilets, and I'll show you a schematic of what we were talking about in a moment, could be easy to build and maintain. If there's a dry toilet, it doesn't need any flushing water, which is a critical thing in a place which doesn't have piped water. There could be some local availability of the dry materials needed. You could think about some management of the actual waste from the dry toilet, either on-site or potentially off-site. And we could think about keeping the the output of the dry toilet and activating it through composting, which is something which also could be done somewhat locally. So part of the challenge in terms of implementing these dry toilets, though, if we were going to do something which kind of put all these pieces together, is that composting can be something that's challenging in this type of environment. The types of environments can be pretty dense, and a lot of times the process parameters need to be adjusted and monitored to be able to get the types of temperatures that you need to be able to get pathogen inactivation. So if you need to be able to, a lot of these composts, to be able to get that type of temperature, needs to be able to get something which is quite large, and it would require a lot of stakeholder engagement and potentially long times for pathogen inactivation. So traditional kind of in guidance and literature says that if you're going to do this type of composting for dry toilets, we would need to have a compost pile, which would be about a cubic meter in size, which is really big. And in many of these areas, which are quite population dense, which could be a potential challenge. So this, we thought maybe the dry toilets could make sense, but this was a big barrier. The fact that if we were going to actually think about achieving pathogen inactivation in the waste from the toilet, having these big compost piles were a big barrier. So this is what the structure that we were thinking about, and we wanted to see, is it possible? Can we think about this type of structure where we could have a toilet which would look something like this? So the idea is that you would, have your toilets. There would be structured in a certain way that when someone used the toilets, the feces would be able to go in one container, and you could structure it in such a way, and there's existing kind of structures within the toilet bowl that enable to have relatively good separation between the urine and the feces. So you could have the urine in one container and the feces in another. And potentially we could think about using, if we could use something that would be about 60 liters, it could, work quite nicely for a household in terms of the amount of time you would need to be able to manage this and the frequency that you would need to manage it. But the problem is that if we were going to use a structure like this, was that in literature, most of what they said and showed for being able to reach pathogen inactivation for this type of composting relied on volumes that are about 1,000 liters. And we wanted to see, could we be able to do something in the volume of about 60 liters? And we wanted to be able to see if we could get it up into a range, in order to get pathogen inactivation. What we wanted to do is we wanted to be able to, in the composting process, get the temperature high enough for long enough that it kills off the pathogens, the dangerous pathogens, which could exist in the feces. And what has been shown in literature, in terms of being able to do that, you need to be able to get up high enough and long enough to be in the top right hand side of this image here on the left. And then to be able to get safely into this image, we chose kind of a design requirement that we could hit. If we could hit 3 days at 55 degrees C, we would be someplace where we could say we were able to do this successful kind of composting at smaller scale. So in this research, we wanted to see, could we get, this compost from 1,000 liters down to 60 liters? And in order to do that, we started with something quite fundamental. We started off with and breaking it down to something fundamental, but at the same time, we wanted to make it something accessible. So we developed an analytical model, which was quite simplified, and we wanted to see if this could help guide us towards getting this type of small compost reactor, which would open up this type of dry toilet technology to the household scale. So this model, it's shown on the slide we have here. It's quite simple. we're just looking at being able to have the individual terms in this model look at, understanding the compost temperature, and it's this compost temperature and the rate that it changes is a function of the mass of compost, as well as the degradation rate of the compost, the container insulation, the evaporation rate of water from the particular compost, and as well as this G, which is aeration, which is how much air we're putting in to this compost. So we tried to boil it down to this relatively simple equation to be able to understand, should we try to size this down? To be able to really understand, we also did a lot of, this is a relatively simple equation, but there's a lot of unknowns in this particular equation. So we also set up a small experimental setup to be able to look at understanding this model and see if we could actually characterize what some of those variables were in our equation overall. So this figure here shows the experimental setup that we have. So on the top right is our compost reaction with it's filled with feces and some dry material sawdust overall. And then we installed temperature sensors throughout the depth of this compost. And in order to provide aeration, we had a pipe which went down through the center of the compost. And then it was just driven with a very simple computer fan. So with the particular model, what we did is we ran this small compost reactor, and we did a relatively small experiment. We wanted to see how small we could potentially make this mass to be able to reach that kind of safety zone of 55 degrees C for 3 days. So we started with some smaller experiments. We ran an experiment here with about 2.4 kilograms and a certain insulation on our container and a certain airflow rate in terms of the actual aeration. So we ran those experiments, and then we used the data and fit our model to that data. And you can see the experimental results here are shown with this gray line here. And then our fit is shown with our black line and then some bounds on uncertainty. So the model is able to fit this relatively small volume quite well. But then we wanted to see, could we use this model to be able to understand where we wanted to go? If we wanted to be able to reach that 55 degrees C for 3 days, what would we need to do? So we adjusted our parameters in terms of mass, thermal resistance, and also our aeration rate, and predicted where we wanted to go. So we predicted, and then we actually then ran that experiment of where we predicted that we wanted to be able to go
silencio, por
to be able
favor?
to reach that 55 degrees C for 3 days. And so we predicted we needed to go up to just over 5 kilograms and reduce down our aeration rate to be able to get that pathogen inactivation conditions. And the figure on the right shows that the model for these other conditions also match pretty well, and with those other conditions we were successfully able to with a relatively small mass and volume get this kind of pathogen activations. This is kind of the first time for these really a very simplified case with very simplified equipment of being able to do this really small volume accessible composting for dry toilets. So our actually working to be able to think about how we can translate these results to different agencies to be able to think about more about design of these types of dry toilets. And we've also done a range of studies to try to understand really what are the design bounds on different sized reactors and aeration rates to be able to have these types of feasible configurations of these dry toilets that will meet these pathogen inactivation conditions. Okay, so I'll touch on one last example of a project currently going on in my group before taking some time for questions. And this is a project actually which we're doing, which is really thinking about closing that design loop, thinking about more about thinking more about technology after it's been developed, how it's being used in a particular context and if it's being appropriately adopted. And this is actually a project that we're doing supporting an organization in Mexico called Isla Urbana. Thinking, how can we, think about technology being adopted in the best way. And where this work really began was actually a few years ago with one of my other students, Sacha Rizante. So we were actually doing some work on different agricultural technologies at that time. And we wanted to be able to think more broadly about this question of adoption. There's a lot of people developing technologies out there, like we're developing the irrigation controller that I was just talking about. But we want, we don't want to just develop a technology for the sake of developing a technology. We want to develop a technology that's going to be used and have the most impact. So in Sacha's work, we went and we looked at trying to understand, are there trends in terms of different factors which will influence whether someone adopts a technology or not? So in order to understand that, we started off with going through and looking at some data from the literature. We wanted to understand, we started with agricultural technologies, and we wanted to understand things in terms of, are there things about the demographics of the adopters? Are there things about the financial conditions of the potential adopters that are influencing whether someone will use a product long-term or not? In order to understand this, we found a number of adoption studies in the literature for different agricultural technologies. We found over 110 studies, and then we found a whole bunch of different different models that people have done to look at for those individual technologies, if someone, the different relationships between these types of variables, and if someone uses their technology long-term. And so this kind of map shows the concentration of where some of these studies were done overall. And we did a number of analyses on these studies. We looked at across different technology categories, different geographies, and we looked at these different socioeconomic kind of factors as well. And we developed, we had to, part of the challenge of doing this work is that we needed to have some way to put all these kind of different factors together and look at the influence of the factors on the potential of being adopted. In order to do that, we developed something called the odds ratio, which is the ratio between which is something which, if it's greater than 1, the probability of the adopting is increased if some condition is true. Okay, so what this means, so for example, here for some of these types of terms, so if someone had 5 years more education than the average, would the probability of adopting be higher? And yes, there was some influence in terms of that term. But when we went across all these different kind of factors, we found, yes, there is some small relationships between different factors and probability of adopting particular technologies. So there's some small relationship between access to credit and people adopting technology, for example. There's some small relationship between people having ownership of their own land and being able to, and adopting a technology. But the main, the biggest kind of factors whether someone would adopt the technology was if they had access to extension workers, or that means basically workers that would be able to support the implementation of the technology, and if they were members of a farmers organization or an organization where they may have support. So we found that there were some factors where they would have more probability of adopting a technology, but we found overall the relationships were not super strong, and that really it was the context which was really the most important piece. We have taken this to start thinking with some partners about really more in-depth thinking about this element of technology adoption. And we've been doing this now for, as really the contextual factors are important, we've been zeroing in on some particular technologies and contexts. And that's what we've been doing alongside Isla Urbana. And this is some work of some students, Erin Rudy and Adriana Patino, really thinking about water access within Mexico. I started off the presentation talking about UN Sustainable Development Goal 6, and there is, in Mexico, there's a significant number of households which are lacking sustainable access to water as well. So in this particular context, there's been a push in some ways to think about the potential of decentralized infrastructure. So in Mexico, a lot of households, as you know, will rely not necessarily only on these intermittent pipe systems, but will have trucked water and bottled water. But there's challenges there. Rainwater harvesting is being considered as an affordable and strategic source where this type of centralized supply is limited. We've been looking at that with our partner organization in a little bit more detail. So we've been working with Isla Urbana, which has installed approximately 45,000 rainwater harvesting systems in Mexico since 2009. And the systems that they've been working on are shown in the figure on the right. You'll have your catchment surface, your roof, and then the water will be captured through the downspouts and fed into a cistern after passing through a first flush diverter. So the first amount of the water coming off the roof is often the most dirty, so it's captured and stored, and then the rest goes into a cistern. And then the water from that cistern can then be used in a large cistern like this. It may be pumped up to a secondary tank on the roof, but every rainwater harvesting system can look a little bit different. So we started this work with Isla Urbana a couple of years ago, and we've been doing this study to try to understand more about adoption of their systems. We're working with Isla Urbana also to understand more about some of the adoption within projects that they've done. They have been working in the state of Jalisco, near Guadalajara, and have installed over 8,000 rainwater harvesting systems in the past several years. And we wanted, to work together with them to understand a little bit about what's happened since they've installed those systems a couple of years ago. We wanted to understand a few things about, are the systems still being used? What are the perceptions of the users of those systems? And also trying to understand more nuances about, what the household's knowledge is of those systems, and also what is the quality of the water, which is actually also in those systems. The elements of those systems I've walked through before, so I'm just in the interest of time, we'll move forward. So we actually, together with Isla Urbana, last summer, we conducted a survey of nearly 1,000 households which received those systems in the past several years in and around Guadalajara. And we found a number of things after going through and doing that survey and visiting households. We found, the questions were about if households had adopted and were still using the system. So I think we found that, and I'll show the numbers in a moment, that many of the households were adopting these systems, but there's different levels of actually adopting. Adopting is not something which is only binary, which is often talked about in the literature. But many households, and really what would be considered the people who are using the systems the best, had not only adopted the systems, but had really adapted them, changed them to be able to meet kind of their own kind of needs, creating other mechanisms to reuse some of the water from the first flush diverter and other elements as well. We also found when we went through, as I mentioned, like adoption is not necessarily binary. So I think different, things, there's differing levels of maintenance in many of the households. Sometimes as a result of the fact that that some of the setups were not necessarily super accessible. Some of them were rather tall and bulky, and those were things which would be challenging for some of the elderly population to actually maintain. Looking at the results of the overall survey, we did find, though, that most of the systems were still set up and still working and still being used to harvest rainwater after 2 years after installation, which is great. So that these would be considered being adopted. And then the ones that were disconnected, most of the households said they were disconnected because they were in the process often of doing some remodeling or changing some things around their house. But one thing that we did find as well, when we were actually looking through some of these systems, as we mentioned, is that there was really a lot of variation in terms of what the quality of water which was harvested were. And we wanted to understand a little bit more about what some of the factors which may influence some of that elements of how well someone was using and adopting the system. So we found that there were, we classified the different quality of water using a visual assessment. And you can see kind of some of the distribution here. There were some households with very clean, but there's across a spectrum of these types of overall water quality in the storage of for these rainwater harvesting systems. And we wanted to understand a little bit, at least from our survey, about what might be influencing the different usage of these types of systems. And one of the things that we did ask in our survey was about the knowledge of the system. We asked people to describe to us about how the system worked. And we found some very interesting results. We found some results that that showed that there is a correlation between knowledde of how the system works and the actual water quality in the actual tank. We found this using a chi-square test, where the figure on the left would show if there was no correlation between knowledge of the system and water quality. But the figure on the right is what we actually had. And if you can kind of see it if you take a look at some of the data, you can see this dark blue line are households which had a correct knowledge of how the system worked. And you can see very little. There were no households which had very dirty water, and maybe one household which had dirty water. But most of those households, for people that knew how to correct rule, were clustered in terms of higher water quality, versus households which had an incorrect rule, had incorrect knowledge, had their distribution skewed more towards having dirtier water. So after going through and actually doing the statistical analysis, we ended up with a statistically significant correlation between knowledge of the system and water quality. So we're thinking more now with Isla Urbana about how we can take this to the next step. We're analyzing some of the other data within the survey to understand what other factors might be related to water quality. And there's a desire also to understand how different training and design influence this, adoption and adaptation elements for some systems. So in order to kind of really understand this in our next steps in the research, as an engineering research lab, we've been looking to understand a little bit more in-depth nuance in terms of how these households are using these systems. So we're actually working with Isla Urbana to do some instrumentation within these systems and understand really how they're being used. This is a quick summary of what some of the work that's been going on within my own research group, and thinking really holistically through this design process, starting with the fundamental approach, and then also thinking about how we can close the loop to be able to develop appropriate technologies to improve access to water in marginalized areas. This is just one project. This is just one project, which is within the broader Center for Global Engineering at the University of Toronto, where we think about how we can think about educating people to think very broadly about these types of problems affecting vulnerable populations. And I want to thank my great team in doing this overall work.
Bueno, muchas gracias, Amy, por esta conferencia tan enriquecedora. Nos ha mostrado la importancia de diseñar tecnologías que sean adecuadas, colaborativas y sensibles a las realidades de las comunidades. Lamentablemente, como vamos un poco retrasados en el programa, no tendremos tiempo para las preguntas y comentarios. Pues deseo a todos y todas un congreso exitoso y provechoso, que las conversaciones que empezamos hoy sigan creciendo y se conviertan en colaboraciones con un impacto duradero, por favor. Gracias. Entonces le paso las palabras al maestro.
Muchas gracias, profesor Yu, Dr. Amy, thank you very much. Y bueno, con eso cerramos esta segunda conferencia plenaria, la primera conferencia virtual, y nos estaremos viendo el día de mañana a través de las sesiones de ponencias virtuales. A quienes nos acompañan a través de las redes sociales y de la plataforma de Teams, muchas gracias. Y pues continuamos con estas actividades del primer Congreso Internacional de Agua Limpia y Saneamiento del Tecnológico Nacional de México. Excelente tarde a todas y todos.